In the 1950s, America's brightest engineers believed nuclear power could put an end to the limits of rail travel, promising locomotives that might run for months without ever refueling. Backed by titans like GM and Westinghouse, Dr. Lyle Borst's X-12 concept was hailed as the dawn of atomic trains. Yet just a few years later, every trace of this bold project was abandoned. Why was the nuclear-powered locomotive never built? And how did a vision meant to revolutionize railroads become an impossible dream? To find out, we have to step into an era fueled by atomic optimism, before the costs and the risks would come crashing down. In December 1953, President Eisenhower addressed the United Nations with a promise that atomic energy would serve the world, not as a weapon, but as a force for peace. His Atoms for Peace speech became a rallying cry for a new age, and the Atomic Energy Commission set out to transform nuclear power from a symbol of destruction into the beating heart of American progress. The Atomic Energy Commission's public campaigns filled magazines and newsreels with visions of limitless, clean energy, reactors lighting cities, powering ships, and even propelling trains across the continent. This was an era when the boundaries of engineering seemed to dissolve overnight. In government labs and corporate boardrooms, nuclear power was treated not as a fantasy, but as the next logical step for nearly every form of transportation. The Atomic Energy Commission encouraged inventors to think big, offering technical guidance and, in some cases, access to subsidized uranium. Trade journals speculated about atomic-powered airplanes and merchant ships, while engineers from General Motors and Westinghouse began to sketch out the possibilities for railroads. Rail executives watched as nuclear submarines slid into the water, and the keel was laid for the NS Savannah, the world's first nuclear merchant ship. The message was unmistakable. If reactors could operate safely beneath the waves and on the high seas, why not on steel rails? The Association of American Railroads, eager to be seen at the forefront of progress, lent its support to feasibility studies. The idea that a locomotive could run for months without refueling, immune to the price swings of coal and oil, fit perfectly with the spirit of the age. In this climate of boundless atomic optimism, the stage was set for the X-12 and its promise to rewrite the rules of railroading. Dr. Lyle Borst, a physicist at the University of Utah, stepped forward as the most determined advocate for the nuclear locomotive. By 1951, Borst had gathered a small team of graduate students to tackle what seemed at the time a solvable engineering challenge, harnessing atomic power for rail. He brought a reputation forged at Brookhaven and Oak Ridge, and his proposal quickly caught the attention of the Association of American Railroads, abbreviated AAR. The AAR saw in Borst's idea a chance to leap ahead of both foreign rivals and domestic competitors, so they agreed to sponsor a formal feasibility study. General Motors and Westinghouse, both eager to stake their claims in the atomic future, offered technical assistance for the study. While neither company committed to building a prototype, their engineers contributed calculations and design reviews, lending the project a degree of credibility that pure academic speculation could not provide. The study, running from 1951 through 1957, became the most comprehensive attempt to map out how a nuclear-powered locomotive might actually work. Borst's concept was ambitious: a 160-foot articulated machine weighing 360 tons, designed to house a uranium-fueled reactor, a steam turbine, and electric traction motors capable of delivering up to 8,000 horsepower. The heart of the design was a 200-ton lead shield to protect the crew from radiation, and a dedicated radiator car to manage the enormous waste heat. Babcock & Wilcox, already a leader in reactor technology, was tapped for the core design. Borst's team calculated that, with government-subsidized uranium, the locomotive could run for months without refueling, a tantalizing prospect for an industry dependent on costly and volatile fuel supplies. Between 1954 and 1957, the feasibility study produced technical blueprints, cost estimates, and performance projections. Yet even as the numbers were tallied and the diagrams refined, the limits of the era's engineering began to surface. The X-12 remained a concept, but for a brief window it stood at the center of serious industrial debate, its backers certain that atomic power could transform the rails as surely as it had changed the world's navies. The X-12's blueprint rested on a simple but radical premise: replace the diesel engine with a compact nuclear reactor and let atomic energy drive the train for months without stopping. At the core of the design sat a small, pressurized water reactor fueled by highly enriched uranium-235. The reactor's job was to heat water directly, producing high-pressure steam. This steam would then flow straight into a condensing steam turbine mounted just behind the shielded compartment. Instead of turning wheels mechanically, the turbine spun a set of 4 compact generators, each about 2 feet wide. Electricity from these generators powered traction motors mounted on 9 axles under the engine car, and 3 more under the radiator car, forming a turbine-electric setup reminiscent of the diesel-electric locomotives then conquering the rails. The entire power chain was laid out to maximize efficiency and minimize stops. With about 11 pounds of uranium on board, the X-12 could, in theory, operate continuously for 2 to 3 months before requiring a refuel, an interval unheard of in conventional railroading. The locomotive's normal output was rated at 7,000 horsepower, with the turbine itself capable of surges up to 11,000 horsepower for brief periods of acceleration. Because the reactor produced steam directly, there was no need for the water tenders or the massive coal bunkers that defined earlier steam giants. The radiator car, stretching 60 to 65 feet, handled waste heat with banks of fans and radiators, closing the cycle and keeping the system sealed from the outside environment. Every engineering choice in the X-12's design aimed to harness the promise of atomic endurance. The direct steam cycle cut complexity and weight, while the articulated frame distributed mass across more axles. For a short window in the 1950s, it seemed plausible that a train could cross the continent without ever pausing for fuel, guided by nothing but the steady pulse of a nuclear core. Railroad engineering has always been a contest between ambition and the hard limits of physics. For the X-12, those limits arrived in the form of weight, specifically the enormous burden of radiation shielding. The locomotive's reactor core, though compact by nuclear standards, demanded protection from every side. Early calculations by Dr. Lyle Borst's team called for a lead shield weighing nearly 200 tons, more than the combined mass of 2 fully loaded diesel locomotives. This was not a luxury, but a necessity. Without it, the crew compartment would have been uninhabitable, and the risk to anyone nearby would have been unacceptable. The shield alone accounted for more than half of the X-12's total weight, which reached an estimated 360 tons across its 2 articulated sections. This figure dwarfed anything then running on American rails. For comparison, a standard EMDF-7 diesel-electric tipped the scales at just 120 tons, spread over 4 axles. The X-12, at 3 times that weight, required 12 powered axles simply to distribute its load without crushing the rails beneath it. Even with this arrangement, axle loads approached the very edge of what North American mainlines could tolerate, about 30 tons per axle, a threshold that left little margin for error. This mass was not just a matter of heavy machinery. It was a direct consequence of the physics of radiation. Every inch of shielding added safety, but also added weight, pushing the design further from practical reality. The articulated frame, the extra axles, and the elongated radiator car were all attempts to spread this burden, but none could erase the fact that the locomotive's mass would stress bridges, tracks, and maintenance facilities far beyond their intended limits. For rail engineers, the numbers on the page spelled trouble, a train that could run for months without stopping, but might never be allowed to leave the yard. The promise of atomic propulsion collided head-on with the realities of steel and stone, and the X-12's blueprint began to look less like a roadmap to the future and more like a warning about the limits of technology. Radiation is invisible, but its effects are measurable. And for anyone working near a nuclear reactor, impossible to ignore. In the 1950s, the Atomic Energy Commission set a strict occupational exposure limit, 5 rem per year, for whole-body radiation. This number was not arbitrary. It reflected a growing understanding that even low doses, accumulated over time, could damage tissue, suppress immune systems, or increase the risk of cancer. For the X-12, every design calculation had to answer the same question: how do you keep the crew and everyone nearby below that threshold? Inside the locomotive, the reactor core would have emitted powerful gamma rays and neutrons, both capable of penetrating steel and concrete. The proposed solution was a 200-ton lead shield wrapped around the core and stretching between the crew compartment and the reactor vessel. But shielding was not perfect. Any gap, any flaw in the assembly, could allow radiation to leak into the cab. Even with the best materials, some exposure was inevitable. Health physicists ran dose calculations for every scenario, including normal running, maintenance stops, and emergencies. Their models showed that at typical distances, a well-designed shield could keep crew exposure near, but not always below, the 5 rem annual limit. The closer you stood, the greater the risk. The problem did not end with the crew. Railroads run through towns, past schools and neighborhoods, and along busy platforms. If the X-12 paused at a station or rolled slowly through a city, stray radiation could reach bystanders on the platform or people living near the tracks. The risk was not just theoretical. Even a small, persistent leak could add up over time, especially for workers who loaded cargo or serviced the train. The 5 rem standard was meant to protect workers, but the public had no such buffer. This turned what started as an engineering challenge into a moral dilemma. How much risk could be justified in the name of progress? For the X-12, the answer was never clear enough to move forward. Shielding a nuclear reactor on rails meant more than just piling on mass. It forced engineers into a maze of hard choices. Lead, dense and malleable, offered the best protection per inch, but it came with a staggering weight penalty. Borated water, used in some naval reactors, absorbed neutrons efficiently, yet it required heavy, leak-proof tanks and constant monitoring. Concrete, the standby for stationary power plants, was simply too bulky for a moving vehicle. Each material promised safety but threatened practicality, and no blend could erase the fundamental problem. Every pound of shielding added to the locomotive's burden, pushing axle loads to the brink of what the track could bear. The shielding dilemma spilled beyond the locomotive itself. Refueling and maintenance required a facility unlike any standard rail yard. Servicing a nuclear engine meant more than swapping out parts or topping off fluids. The entire reactor compartment, still hot with residual radioactivity, would need to be handled inside a hardened depot modeled after the containment buildings of power plants. These depots had to be remote, with thick walls and controlled access, equipped for everything from fuel transfer to shield inspection. Every tool, every surface, had to be monitored for contamination, and spent fuel demanded secure storage until it could be safely transported away. Routine maintenance, a daily reality for diesel engines, became a logistical puzzle for the X-12. The direct cycle design meant that turbines and piping exposed to radioactive steam could not be serviced in the field. Components would either be left untouched for years or swapped out entirely by teams trained in radiation safety, working behind barriers, or with remote manipulators. Even minor repairs required planning that rivaled a nuclear plant's outage schedule. This system-wide complexity changed what it meant to operate a locomotive. The X-12's promise of endless range hit a network of specialized depots, hazardous material protocols, and a maintenance regime that stretched far beyond the rails. Shielding was not just a technical detail, it was a burden that rippled outward, touching every aspect of railroad operations and raising the stakes for what could happen if anything went wrong. A nuclear locomotive derailing at speed posed a nightmare scenario that engineers struggled to quantify. Impact modeling from the period suggested that, at 60 miles per hour, the forces unleashed in a major crash could compromise the integrity of the reactor vessel, especially if the train struck a bridge abutment or jackknifed into a ravine. While the X-12's design called for a thick, 200-ton lead shield, an automatic reactor shutdown on collision, containment was never absolute. Early estimates placed the probability of a catastrophic breach in a high-speed derailment somewhere between 1 in 1,000 and 1 in 10,000, a low number, but not zero. In the event of a rupture, radioactive steam and contaminated water could be vented directly into the environment, spreading across trackside neighborhoods and farmland. Emergency planners calculated that cleanup would require cordoning off miles of track, evacuating entire communities, and removing tons of contaminated soil, an operation measured in years, not weeks. The sheer scale and cost of such a disaster forced railroads and regulators to confront the unthinkable. One accident could turn a routine freight run into a radiological crisis, stretching far beyond the rails. By 1954, the numbers on the X-12's balance sheet told a story no rail executive could ignore. The projected cost to build a single nuclear-powered locomotive stood at $1.2 million, twice the price of a 4-unit diesel set with similar hauling power. For railroad chief financial officers, that was only the starting point. Each X-12 would demand a custom-built reactor core, a 200-ton lead shield, and a specialized maintenance regime, costs that ballooned far beyond the sticker price. Operating expenses added another layer of uncertainty. While uranium-235 fuel was theoretically subsidized, its price was both classified and unstable, and the logistics of sourcing and handling nuclear material introduced expenses that no diesel fleet manager had to consider. Insurance companies, faced with the prospect of a mobile reactor crossing state lines and running through cities, balked at providing coverage. Premiums, where quoted, approached sums that would wipe out any long-term savings from reduced refueling. Even before the first prototype was built, the X-12's financial burden had outpaced any promise of atomic efficiency. For a railroad industry already investing heavily in proven diesel technology, the nuclear locomotive was simply a bet too risky to place. By the late 1950s, the American railroad industry was already in the midst of a sweeping transformation. The introduction of the EMD-FT diesel locomotive in 1939 had set off a wave of dieselization that moved faster than anyone predicted. By 1955, diesel electrics hauled more than 90% of all rail freight in the United States. Railroads found that diesel units cost less to buy, needed fewer mechanics, and could be refueled in minutes rather than days. The numbers left little room for debate. A 4-unit diesel set delivered the same horsepower as the X-12, but at half the price and a fraction of the complexity. At the same time, public attitudes toward nuclear technology began to sour. The 1957 Windscale fire in Britain, the worst nuclear accident of its era, dominated headlines and stoked fears of radioactive fallout. Newspapers ran editorials, warning of the dangers of mobile reactors, and community groups petitioned regulators to keep atomic engines away from populated areas. The combination of proven diesel reliability and a growing tide of anti-nuclear sentiment made the prospect of a nuclear-powered locomotive less a vision of progress and more a public relations liability. Regulators and insurers took notice, and the final barriers to adoption became insurmountable, not just technical or economic, but social and political as well. Nuclear-powered trains never left the drawing board, but their story still echoes today. As clean energy and infrastructure debates intensify, the balance between technological ambition and public safety remains unresolved. Every bold solution faces old questions. What risks are we willing to accept for progress? The future of transport depends not just on what we can build, but on what we choose to trust. Let me know your thoughts in the comments.